So, so today we'll start with a new topic, that is the design of ground storage reservoir. So basically, these are nothing but the underground tanks, and your underground tanks they can be of various shapes. Either it will be circular in nature, or it can be even rectangular in nature. Okay. So in this today's class, we will focus on the circular water tank. Okay, which is there inside the ground. Okay, so this is the problem statement. So please note it down that we have to design the GSR, that is ground storage reservoir, for a capacity of 100 meter cube. So this is the capacity. So in the examination also this capacity will be given to you. Okay. Now, second and the most important part which is given in the problem, that is the height of the water. Okay, this is not the height of the tank. This is the height of the water. Okay, so height of the water is 3 meters. Okay, then the FSL is equals to GL. So FSL means whenever the water is full, so the whatever level is there of the water, it is same as the ground level. So this is the meaning of that. So water in the tank can reach up to only the ground level only. Okay, not the above the ground level. Then the SBC of the soil is given to you as 100 kilonewtons per meter cube. So definitely on the site you have to go and you have to find out the SBC using experimentation, and that value you have to use. Okay, so this value is given over here. And as far as concrete grade and steel grade is concerned, so this is given to you as M25 grade concrete and Fe415 grade steel. Anyway, these are the minimum grade of concrete and steel which you have to assume for the design of any environmental structure. Okay, you can even go for higher one, but this is the minimum. M25 is the minimum grade of concrete. Then another parameter is given to you, that is the rise of the dome is nothing but the diameter of the dome divided by 10. So in short, we are basically going for a structure which is having a dome covering. Okay, so slab covering we will cover in some other portion. So here there is a dome, and whenever there is a dome, so dome is basically curved structure, and we have to give the rise for that. Okay, so that rise is given to you as the 1/10 of the diameter of the tank. Okay, so this is the data which is already given to you. Now, as far as this part is concerned, designing is concerned, we have to use IS 3370 part 2, which I have already shown you in the previous lecture. And as per IS 3370 part 2 2009, so the values has to be taken which are highlighted in the red color. So since we are using M25 grade concrete, so the permissible tension in the concrete under the direct tension is given to you as 1.3 here. Okay, so this is 1.3 newtons per mm square. As far as bending tension is concerned, for bending tension it is 1.8 newtons per mm square. Okay, so this is as per table number 1 of IS 3370 part 2 2009. Okay, then the permissible stresses in concrete under the compression. Okay, so this was under the tension, you can see this was under the tension, whereas this portion, that is table number 2, is for the compression. So for the bending compression, okay, so the value of this bending compression is for concrete M25 it is 8.5, and for the direct compression the value of the permissible stress is 6. Okay, so here you can see this is sigma CBC and sigma CC. See, this is sigma CBC and this is sigma CC. Okay, and usually we call this as sigma CT, that is stress in concrete under tension. Okay, direct tension, right? और ये वाला जो है, this is sigma BT. Okay, so this is sigma stress in concrete in bending tension. Okay, so these values you have to remember, because based on these values you have to find out the design constants. Okay, so let us proceed further. Now there is another table, that is table number 4, and table number 4 deals with the permissible stresses in steel. Okay, so we are using the steel, we are using the main reinforcement as HYSD bars. Okay, and distribution reinforcement you can use the mild steel bar. and as per this table, the sigma st value. Okay, so this is your sigma st value. So sigma st value for high strength deform bars, that is HYSD bar, this is nothing but 130. So this is sigma st. Okay, and this value is for the sigma st value is for the mild steel bars. Okay, so using these values, now we have to find out the design constants, and these design constants will be used for the further calculation part. Okay, I hope this is clear to everybody. Okay, fine. So let us continue. Now, in the working stress method, you have to find out the design constants like modular ratio, K, J, and Q. Okay. So from this table, you have already found out the sigma CBC value as 8.5 newtons per mm square. Okay. So this is your sigma CBC value, and this is nothing but your sigma ST value. Okay. So these are the values taken from the IS course, right? Now, depending on these values, now we have to find out the design constant. So the first design constant is the modular ratio. Okay. So this is your modular ratio. So modular ratio is nothing but something like 280, okay, divided by, this is 3 into sigma CBC. So sigma CBC value is 8.5. Okay. So can someone tell me how much is this value, please? Sorry, 10.98. Okay, so the modular ratio, now we have to use 10.98. Okay, on the similar lines, now we have to calculate the value of K. So K is nothing but 1 upon 1 plus sigma ST. Sigma ST is 130, M is 10.98 into your sigma CBC value is 8.5. So how much is this? 0.418. Okay, so on the similar lines, you can calculate the value of J also. This is 1 minus K value is 0.418 divided by 3. Yes, 1.0 0.86. Okay, and your Q value is sigma CBC, which is 8.5 divided by 2. J is 0.86 into K is 0.418. Somebody? 1.527. So these are the design constants for M25 grade concrete with Fe415 grade steel for the design purpose. Okay. So now let us proceed further. So let us first of all find out the dimensions of the container. Okay. So we have a tank, and tank has got different components. So in the figure, you can see over here, this is your top dome. Okay, so this particular portion is called as top dome. This is the ring beam. Okay, so this ring beam is basically the purpose of this ring beam is to resist the tension which is caused due to the bending of the top dome. Then we also have the cylindrical wall. Okay, cylindrical wall, and then lastly we have a slab. Okay, so this side we have a slab. Okay, please draw this figure correctly. I hope picture is clear to everybody. थोड़ा कलर का प्रॉब्लम होगा, बट आई थिंक यू कैन मैनेज, है ना? Okay, shall I continue? So the so as per the problem statement, the height of the water is already given to you, isn't it? So the height of the water, so when I say the height of the water, I'm talking about this height. Okay, so this height is given to you as 3 meters. Okay. So now when we are finalizing the dimensions of the container, definitely height of water is going to play a very important role. But apart from that, we have to assume some freeboard. So if I take a straight line which is like this, so this much portion is called as freeboard. Okay, so this freeboard you can assume as per your convenience. Mostly the freeboard of 1 feet, that is 0.3 meters, is considered. Okay, so if you want, you can change it as per the choice of your owner or as per the requirement. So this freeboard, we are assuming this as 0.3 meters. So this makes the height of the tank. So here I'm saying h, there are two things, one is h and one is hw. HW is nothing but the height of the water and H is nothing but the height of the tank. So the height of the tank becomes, this will be HW is 3 plus freeboard is 0.5. So the total height, so I'm talking about this height. So from here to here. So this height is now becoming 3.3 meters. Okay. So this is what we are assuming right now, right? So now if I choose these dimensions, okay, so I can take the, I can find out the diameter of the tank over here. So here, let me write down this over here. So volume of the tank is something like 100 meter cube, which is given in the numerical itself. And volume of a cylinder can be calculated in a way that is pi by 4 into d square into height of the water. Okay, so height of the water is already known to you because this is given. So this height is basically 3 meters. Okay, so from this, can you tell me what will be the diameter? Sorry, 6.211. कितना है? 6.514 बराबर है, ठीक है. So this is 6.514. So what I am doing, that is the diameter of the tank here in place of 6.514, because I cannot provide exactly 6.514. So I am assuming as 6.2 meters. Okay, so this diameter. Okay, so if you see the innermost diameter, क्या कर रहे हो यार तुम लोग, अलग अलग बता रहे हो. Sorry. Oh, sorry. My mistake. 6.6. Sorry, yeah. 6.6 meters. ठीक है अभी? ठीक है. So this is your 6.6 meters. नहीं, हाइट ऑफ टैंक नहीं लेना है, हाइट ऑफ वाटर लेना है. तुम लोगों ने क्या लिया है? हाइट ऑफ वाटर ही लेना है, हाइट ऑफ टैंक नहीं लेना है, बिकॉज हाइट ऑफ टैंक कंसिस्ट ऑफ हाइट ऑफ वाटर प्लस फ्रीबोर्ड. ठीक है, अभी आगे बताता हूँ मैं. ठीक है. So right now what you are getting is the diameter of the tank at 6.6 meters. Okay, so let me write down the units also. 6.6 meters, right? So we have to define, or we have to decide the thickness of the tank. Okay, thickness of the tank wall rather. So generally a thumb rule is there that you take the thickness of the wall as 30 times height of the water plus the 50 mm. Okay, so here if you say the thickness of the wall is nothing but 30 into height of the water is 3 meter plus 50, how much is this? Sorry, 140, right? Okay, so we cannot provide 140, we can provide 150 millimeter thick wall. I hope this is okay. Okay, so tentatively we have now decided that the diameter of the tank is 6.6 meters and the thickness of the wall is, let us say, 150 mm. Okay, so now let us see. Now this circular wall is, yes, any issue? So whenever there is a water which is inside, the circular wall will be subjected to expansion, right? And this expansion will be greater as you move down, because as you move down the water pressure is going to increase. but at the same time when you move down, you have a foundation at the base. So the foundation will not allow you to expand, or the circular diameter or the circular portion of the tank, it will not allow to expand. So as a result of this, you can see in this figure, so your tank will be subjected to a behavior which is something like this, because at the base it is fixed. Okay, and in somewhere in between you will get the maximum uh, expansion. Getting it? Can you visualize this? Okay. So for this much of, or for this kind of behavior, now we have to design the wall. Okay. So because of this water pressure, your wall will be subjected to axial tension. Okay, because the diameter is increasing. Then it will be subjected to bending, because if you see this figure, this vertical side is now changing its shape. So definitely along this side it will be subjected to bending, and lastly it will be subjected to shear because horizontal pressure is there. So now we have to design this wall for bending, shear, as well as for the tension. So for this purpose, we have to use different tables which are given in IS 3370 part 4. Okay, so all those tables are design tables. This is as per clause number 3.1.1, page number 9 up to page number 10. Okay, so now let us go for the design of wall one by one. So let us see the design of tension, design of wall under the tension. So for this purpose we will be using table number 4 of table number 9 of IS 3370 part 4 1967, the older one. Okay, so this table looks like this. Okay, so if you see this, the title of this table, it shows that tension in the circular ring wall, comma, fixed base. Okay, one is fixed base, second is free at top. Okay, then and subjected to triangular load. This is what is our case. Okay, I'll once again repeat: tension in the circular ring wall with fixed base, free at top, and subjected to triangular load. Okay, so the figure which is shown over here, so the height is given. Okay, small h is given, and the water pressure is also given. So from this expression, you have to now calculate the tension in the wall using a coefficient multiplied by W multiplied by height multiplied by R. Okay, where R is nothing but this. Okay, so this is nothing but the clear radius of the tank. Okay, so now if you observe very carefully, this table is divided into many parts. So if you see the first column, it is h square by dt column. Okay, so you have already defined the dimensions of the tank. Okay, so you know the value of height, you know the value of diameter, you know the value of thickness. Okay, so using these three values, you have to find out what is your h square by dt value, and correspondingly you have to take the rho. Okay, so now what is your h square by dt value? So here there is a trick thing in which you need to understand, right? Now remember, if I go back over here, I have taken the height of the water as 3 meter. Okay, but I have taken the height of the tank as 3.3 meter. So if you construct this wall, owner can go up to 3.3 meter. तो जब भी उसको पानी भरना है, he can go up to 3.3 meter. If you use 3 meter, you will be getting a quantity of 100 meter cube. But if user wants to have more water, he can even fill up to 3.3. So ideally, you should design the structure for 3.3. Although you have estimated the dimensions for 3 meters, you have given additional freeboard, but there is a possibility that water may reach up to the bottom of the dome, isn't it? So we have to design for that particular room. So here what this particular table shows, this h is nothing but the height of the water. So here I am not taking height of water as 3. I am taking height of the water as 3.3. Okay, intentionally, because water may go up to 3.3, right? So if you use this, so your h square by dt, so h is nothing but 3.3 square. Diameter, how much we have taken? I think 6.6. Okay, so this is diameter is 6.6, and the thickness, so thickness is I think 0.15. Okay, so how much is this h square by dt value? 11. ठीक है, so your h square by dt value is 11 point कुछ है आगे, एग्जैक्ट है, ठीक है. So now if you refer this table, okay, so you can find the h square by dt value. It is starting from 0.4, then 0.8, 1.2, 1.6, then 2, then 3, 4, 5, 6, then 8, 10, 12, and so on. Okay, so if your h square by dt falls under any of this, then you have to go for the interpolation. Okay, so right now we can see our h square by dt value is 11, and it is coming in between 10 and 12. Okay, so now what you have to do is you have to find out what is the maximum coefficient, right? Because if you see this equation, the T, that is the axial tension, can be calculated by equation that is coefficient multiplied by W into H into R, correct? So now which coefficient you have to take? Because as you move from top to bottom, coefficients are changing because your tension is changing. Just now we have seen in the animation that maximum tension will be there somewhere from the bottom, isn't it? So we have to consider that maximum tension. Okay, because if your structure is safe for maximum tension, definitely it will be safe for the upper region as well as for the lower region, right? So now what you have to do from this figure, you have to find out what is the maximum coefficient value. Okay, so now if you see, this is the minus value, okay, this is negative value, this is also negative value, but if you see the magnitude, it is 0.01, it is very small. So as you move away, your coefficient is increasing, here also increasing, here also increasing, increasing, here it is coming out to be maximum, and then further it is reducing and reducing. बराबर है? So this is your maximum value. So maximum value is 0.608 at a distance of 0.6 h, which is measured from top to bottom. Okay, these are the values which are there from top to bottom. Okay, तो ऊपर से 0.6 h पे तुमको सबसे ज्यादा टेंशन मिलेगा, ठीक है. Similarly, if you see the row of 12, so h square by dt value is 12. So here you see this value is increasing. Here also it is increasing. Here also it is increasing. Here it is increasing. But here this is maximum. Okay, this is your maximum, and here then it is increasing and reducing and reducing. Okay, so here you see the maximum values over here, and here it is maximum values over here. So there is some translation in between. So the location is also changing. Okay, so in such case, what you can do, if you observe very carefully, the difference between these two values is not that much, because you see this is 0.628 and the other value is 0.633, is not that much. Okay, so what you can do is you can interpolate between these values. Okay, so now you have to find out, let us say for 10 you have a coefficient of 0.608, and for 12 you have a coefficient of 0.628. Now I want all of you to find out what will be the coefficient in between. Sorry, 618. So this value in between will be 0.618. Okay, so this coefficient will be 0.618. So you can use the equation which is given over here, that is coefficient into W into H into R. So here I am going to use coefficient as 0.618 multiplied by the density of any liquid. Okay, right now we are using water, so this tank can be used for any other purpose. So petrol is there, you have to take the density of the petrol, isn't it? So density of the water I am taking, so this is 10. Now here H, so this H I am taking as 3.3, not 3, because we are considering the worst possible scenario. So the height of the water can reach up to 3.3 into radius. So the radius is nothing but diameter divided by 2. So diameter we have already calculated as 6.5 divided by 2. So how much is the tension now? Yes, someone please. 67.3 kilonewtons, right? So this is 67.3 kilonewtons. Okay. So now you see, if you use the table, so for this portion, that is when you are at a level of 0.6 H from the top, you are getting the maximum hoop tension. So if you move away, that is either to the upper side or to the bottom side, your tension will be definitely less because the coefficient values are getting smaller. Okay. So we need to find out whether the thickness of concrete which we have assumed, which is 150 mm, whether it is sufficient enough to resist this particular tension or not. Okay. If it is not sufficient enough, then what will happen? The cracks will be developed and your structure is going to collapse at that particular section. Okay. So for this purpose, now we have already calculated the hoop tension. So maximum hoop tension. So directly you can have the AST value over here. So the hoop tension we have calculated 67.3. So this is 67.3. So kilonewton is 10 raised to power 3. Now this sigma st, that is the permissible strain in steel under direct tension. Okay, so I'm just turning back a little bit, and if you see the values, so under the, if you read the table very carefully, this is column number 2. So the tensile stress in member under direct tension, comma, bending and shear. So irrespective of whether it is direct tension or bending tension or shear, you have to take these values. Okay, so we are using HYSD bar. So HYSD bar, the direct tension comes out to be 130 newtons per mm square. So here I am just going to write down something like 130 newtons per mm square. So how much is the AST required over here? 5 517, राइट? ठीक है, 518 कर रहा हूं मैं, ठीक है, 518 millimeter square, right? Now there is a clause in the IS code about the minimum cross section area. Okay, so this I have already explained you in the previous class. So this is under the clause number 8.1.1, and if you read carefully, it says the uh, to minimum cross section, minimum reinforcement can be further reduced to 0.24% for the deform bars. Okay, so we can take the minimum reinforcement for the deform bars, and that percentage can be reduced to 0.4% for mild steel bars when any of the dimension of the tank is not more than 15 meters. तो हमारा जो टैंक है उसका डायमेंशन कितना है? 6.5. So definitely we fall under this particular criteria. Okay, so from this clause we are taking the minimum reinforcement criteria as 0.24% of the cross section area. Okay, so I'm going back over here. So 0.24% of the cross section area, so this comes out to be 0.24 divided by 100. Now the cross section area, the thickness is 150 and the wall is per unit. So how much is this? 360 I suppose. बराबर है? Okay, so of course we have to provide the maximum reinforcement. So in case of 360, we have to finalize the 518 millimeter square of cross section of steel along the circumferential direction. Okay, now so this we are finalizing. So this is 518 millimeter square. Okay, so now can you tell me, if I take 10 mm dia bars, spacing will be how much? How much will be the spacing for 10 mm dia bars? Come on, hurry up. 150 नहीं एग्जैक्ट बताओ. 11 और कोई बताओ. 151 और कोई. 151. ओके, सो दिस इज 151. ओके, तो ये ऑलरेडी काफी ज्यादा है. ठीक है, सो व्हाट यू कैन डू इज देर इज वन वे ऑफ गिविंग द स्टील. ओके, so what you can do is you can go for 10 dia bars at 150 center to center in this pattern, ये वाला. Okay, so this will be your 150 center to center and this will be 10 dia bars. ठीक है, so one way you can do it and you can provide the reinforcement only on the one side. Okay, and which side you have to provide? So you can see the highlighted second line in the wall slabs less than 200 mm. Okay, so we have a wall which is having less than 200 mm in thickness. The calculated reinforcement may be placed on one face. ठीक है, तो in place of providing the reinforcement on both the sides, we can also provide the reinforcement on the one side itself. So one way of providing the reinforcement is 10 dia bars at 150 center to center, which is shown on the left hand side. Okay, otherwise you can provide the reinforcement on both the sides. Okay, so if you want to provide the reinforcement on both the sides, so let us say we are providing 518, but in place of 10 dia bars, can you tell me how much will be the spacing for 8 dia bars? 97. Okay, so this is 97. Okay, so 97 if you multiply it by 2, तो ये आता है कितना, 7 दूने 14, 194. ठीक है, so what there is another way of doing this is, in place of this 194 can be rounded off to 175, lowest possible figure in multiples of 25. So what you can do is you can provide this as 8 dia bars, 8 dia bars like this. Okay, this is at 175 center to center. This one is also at 175 center to center, but if you see the distance between this and this will be 175 divided by 2. So if you are providing the reinforcement on both the sides, so you can divide the spacing. So if you wish, you can provide the reinforcement in this pattern or the pattern which is given on the right hand side. Both ways possible. Okay, why I'm telling you this is, sometimes your thickness is more. Okay, because IS code permits us to give the reinforcement only on the one side if your thickness is less than 200. But once your thickness crosses 200 mm, you have to provide the reinforcement on both the sides. Okay, so in that case, what has to be done? That's why I'm telling you this. So you can provide this way or that way. It's up to you. Okay, in wall which is having less than 200 mm thick, there also you can provide the reinforcement on both these sides. Provision is there, but you should know. That's why I'm telling you this. Okay, so now for the time being, let us finalize this. Okay, that is 10 dia bars at 150 center to center. So you can see these circles which are there, those represents the 10 dia bars at 150 center to center. Okay, so how much will be the AST provided now in this case? कितना आएगा? जैसे तुमने स्पेसिंग कैलकुलेट किया था वैसे AST प्रोवाइडेड कैलकुलेट करो, कितना आएगा? Sorry, 523.6. Someone please check. Okay, this is mm square. okay, and this should be less than 518, okay. So this should be less than 518 millimeter square. Definitely, sorry, not less than, greater than. My mistake. This should be greater than. Okay. So what is required and what we have provided, so you can see 518 is required and you have provided 523, so just sufficient enough, okay. So now we have to check what is the stresses in the concrete under tension. So for this purpose the tensile stress has to be calculated, and you have already calculated the maximum hook tension. This is 67.3 into 10 to the power 3, okay. Area of the concrete, so area of the concrete, can be calculated as 150 into 1000, बराबर है. This modular ratio I think you have already calculated earlier. So your modular ratio M is 10.98, okay. So let me go back. Modular ratio is your 10.98 and your AST value is 523.6. So how much is this stress now? Yes, someone please tell me the value of stress. किती येत आहे? 0.43, okay. So this is coming out to be 0.43 newtons per millimeter square, and definitely this must be less than the permissible stress in concrete in direct tension, okay, that is sigma ct. And if you refer back, so you can see over here the sigma ct value over here, this is 1.3, okay. So your value or your wall is safe under the tension, okay. But here you see you have slightly given the higher value of thickness, because you see sigma ct is 1.3 permissible and what actual you are getting is 0.43. This is almost double से भी थोड़ा सा ज़्यादा है ना. So what you can do at this moment, you can reduce the thickness of the wall, ठीक है, so that you can achieve some economy. But if you reduce the thickness of the wall, what is going to happen? Your h square by dt value is going to increase, because thickness is there in the denominator. So definitely the entire table is going to get changed. You have to redo the entire calculations, and then again you have to check whether your wall is safe in tension or not, okay. So in practice you have to optimize this, okay, and then only you can finalize this, okay. So for academic purpose this is okay, this is safe, but if you see economy point of view, this is not good. You are getting much more safer design as far as the permissible stresses in tension is concerned, okay. So anyway, let us go ahead with this, okay. So our wall of 150 mm thick is sufficient enough to resist the axial tension, okay. Now let us talk about the bending, okay. So remember your wall is going to bend like this, okay. So at the 0.6 h measured from the top, you are going to get the maximum tension. So your this circumference of the wall at that level is going to get increased, and because of that your wall is going to get bent, okay. So now IS code has given a table to calculate the values of bending. It is in the same lines with the earlier table, that is table number 9. So this table number 10, you just read the title carefully. This is the moment in circular cylindrical walls, okay, with fixed base free at top and subjected to triangular loading. This is what is our case. Okay, so this is table number 10. So if you refer the equation which is given on the left hand side, the moment is calculated as coefficient multiplied by W multiplied by H to the power 3. Okay, H to the power 3. So again in the same figure you can see the first column is H square by dt value. So we have to refer to the H square by dt value, and accordingly we have to see the table. So we have already calculated H square by dt value as 11, isn't it? This was 11. So for this purpose, again now we have to see the values. Okay, now you see the bending can be positive or it can be negative. Okay, so we have to find out what is the maximum coefficient. So if you refer this value, if you see the 10th row over here, this is 0, this is 0, this is 0.1, this is positive. Okay, this is 0.0001, then this is 0004, then 7, then 19, then this is 29. So as far as this is concerned, positive values are concerned, you are getting the maximum positive value over here. Okay, but if you refer the negative value, कौन सी वैल्यू ज्यादा है? Negative value. If you forget the sign, okay, if you forget this sign, so you will find the maximum bending is occurring at the base. Getting it? So we have to design the wall for the bending. So for this purpose, whether it is bending on this side or bending on that side, whether it is negative or positive, your thickness should be sufficient enough to resist the bending. Okay, so if you see the row of 10, you are getting the maximum value at the base of the tank, and if you see the similarly on the row of 12, okay, so this is your row of 12. So in the row of 12 also you will find the maximum coefficient is there at the bottom. Okay, because here you see the maximum value is somewhere over here, maximum positive value. बराबर है? But still if you compare this value with this, this is smaller and this is larger. So now we have to go for the interpolation. Okay, so for 11, how much will be the value? Someone please tell me. कितना है? 0.011 kilonewton. Sorry, not this one. This is a coefficient, right? So it doesn't have any unit. Okay, so the coefficient is 0.0113. Okay, so now as per the equation which is given in the IS code, now you can calculate the values of the bending moment. So here the coefficient is 0.0113, density is 10, and the height, so here height should be taken as 3.3, not 3. Okay, so can you tell me how much is this value, please? Bending moment value. Sorry, 4.06 kilonewton meter. So you see the maximum bending moment which is occurring at the base, its numerical value is very small, बहुत कम है. 4.06 is almost nothing. ठीक है, but still as per the design process we have to find out what is the reinforcement and what is the depth required to resist this much of bending moment. Okay, so now with this 4.06, now we have to go for the this one. So your maximum bending moment is 4.06. Okay, this is kilonewton meter, and this will be same as moment of resistance. And for the working stress method, moment of resistance is nothing but QBD square. Okay, so now I'm just expanding this expression. This is 4.06. This will be into 10 to the power 6. So the value of Q, I think we have calculated the value of Q as 1.527. Okay, so this is 1.527 into B. Okay, how much B I have to take? 1000. Okay, this will be 1000 and depth. So depth of the this depth is nothing but the thickness. This I have to calculate. Okay, so how much is the D now? It will be very less. 51 point बराबर है. Okay, so this D is coming out to be 51.56 millimeters. Okay, and what actually thickness we have provided? 150 mm. So definitely this is safe. This is also indication that your wall is designed on very higher side. So 150 is not required. 51 is sufficient. In the actual tension also we have seen the permissible stresses are almost more than double. है ना? So this way you can come to know that your structure is designed for oversafe. It's basically it's oversafe. So you can redesign it if it is required. Okay. Anyway, so let us go for this. So now what I can do is our capital D is 150 mm. Okay. So D plus clear cover. Okay. So let us keep clear cover as say 25 mm. Okay. So if you go for this, so your this, that is the depth, effective depth will be something like 125 mm. This is nothing but your D. ठीक है ये? Is it okay? So total depth, capital D is 150. Okay, so let me write down over here. So capital D is 150. Okay, clear cover I am taking this as 25. So effective depth is I think 150 minus clear cover minus you take generally the diameter of the bar, half of the diameter of the bar. So I am taking the 10 mm dia bar divided by 2. So effective D तुम्हारा कितना आएगा ये? 120 बराबर है. Okay, forget about this for the time being. Okay, so you just take the small value of D, small d value as 120 mm. So let me write down over here. This will be 150 and this will be 120. Okay, so now with this, now you can go for the AST calculation. So maximum bending moment is 4.06 into 10 to the power 6. Okay, divided by sigma ST. Definitely this is 130 into J. J कितना था? J is 0.86, right? Right. So this is, and D is 120. How much is this? भाई बताओ कितना है, AST कितना है? Sorry, 302. Yes, someone please confirm. This is 302 millimeter square. Okay, so if you see the AST minimum, so AST minimum is 0.24% of the cross section area. That comes out to be 360 millimeter square. In the previous design also we have seen. So definitely we are going to provide the maximum value. So in this case, the AST minimum is the maximum value. So we can go with the AST as 360 millimeter square. And if you take, let us say 8 mm dia bars. Okay, how much will be the spacing? Sorry, 139.62. So this is 139. तो इसको हम लोग करते हैं 125 center to center. ठीक है? So remember we have given the drawing. We have finalized the drawing, the one which is there on the left hand side. Okay, so we have provided the reinforcement only on the one side. So definitely we have to provide the reinforcement, the other reinforcement, vertical reinforcement on one side only. So basically, if you see this figure, so the vertical reinforcement in this picture, it will be shown as the circular dots. Okay, so this reinforcement will be something like, so this will be 8 dia at 150, 150 था ना ये? Sorry, 125. Okay, not 150, this is 125 center to center. Okay, this will be the vertical reinforcement. This is top section which we have showing over here. Okay, so this way we have to provide the reinforcement. Is it okay? Now once everything is set, now we have to find whether the bending stress, whether it is in permissible limit or not. Okay, so bending stress can be calculated as the maximum bending moment divided by section modulus, that is Z. Okay, so bending stress, I think we have calculated as something like 4.06. Okay, into 10 to the power 6, and Z is, Z क्या होता है बताओ? What is Z? BT cube by क्या होता है? I by Y. I by Y. BD square by 6. So this is B, D square by 6. B is 1000, D is 120. Okay, and this is divided by 6. So can you tell me what is the bending stress? Sorry, 1.69. Someone please cross check. So this is just a margin. Okay, so bending stress is 1.69. It is very close to 1.8, but it is still safe. Okay, so we can say that yes, 150 mm thickness is sufficient enough for us to resist the given load. Okay, is it fine? Okay, so let us quickly continue. Let us see the third component of wall design, that is the design for shear. Okay, so for this purpose we are using IS 3370 part 4 1967 and table number 11. Okay, so the title of this table number 11 is shear at the base of the cylindrical wall. Okay, so as you move from top to bottom, the water pressure is continuously increasing and maximum pressure will be there at the base of the wall. So there are three conditions which are given. The very first condition is the triangular condition, so where you have a triangular load. Okay, so in our case there is a water pressure, so it comes under the category of triangular load. So it says the V, that is the shear force V, is equals to coefficient multiplied by W into H square. Okay, the unit here it is written in kgs because in 1967 IS code the value of W was taken in kgs, but this time we are taking in newtons, so automatically it will be in newtons. So your coefficient multiplied by W into H square. Okay, now if you refer this table, the first column is again H square by dt value. Okay, so everything is depending on H square by dt value, and the second column is the triangular load with fixed base, which is our case. The second is rectangular load is fixed base, that is not our case. Then triangular or rectangular load with hinged base, अपना hinged base नहीं है. Okay, and there is a moment at the edge. So all those tables are there. We have to refer the second column. Okay, so if you refer the second column, you have the H square by dt value as 11. Okay, so 11 falls under this, in between this one. So we have only two values. So for 10 the value is 0.158 and for 12 the value is 0.1. 146. So all we have to do is interpolate and find out the coefficient. बताओ. Sorry. 0.153. Okay. And equation to calculate the shear force is also given in the IS code itself. So please calculate the value. So here V can be calculated as coefficient, which is 0.153. Value of W will be 10 and H square. So H you have to take as 3.3 square. So how much is the shear force? Sorry. 16.16.66, right? So this is 16.66 kilonewton. Okay. So now for this purpose, again we have to check for the shear stress. Okay. So the shear stress can be calculated in the same form, that is V divided by B into D. So 16.66 into 10 to the power 3 divided by B is 1000 and D is 120. Okay. Yes, tau V value someone. 0.138 newtons per mm square. ठीक है. So now this is the value of the shear stress. Now you have to calculate the percentage of steel. Okay. And depending on the percentage of steel, now you have to find out whether it is safe in shear or not. You don't have to do this, because you see, if you refer the table and if you see the first value of tau c, okay, the first value of tau c is 0.19. ठीक है. So if your percentage of steel is 0.15, okay, the corresponding percentage of steel, or even if it is less, the tau c value has to be taken as 0.19. बराबर है. ठीक है. अगर तुम्हारा परसेंटेज ऑफ स्टील बढ़ता है तो टाउ सी तुम्हारा वैसे ही बढ़ रहा है. But and what actually tau v you are getting is 0.138. So definitely as such this is safe. So even if you calculate the percentage of steel, you will find out the value of tau c is greater than tau. This is for sure. Okay, but still you complete the calculations. Okay. So now here you see which AST you will be taking, because we have provided AST for bending as well as the AST for the tension. Okay. Here when the wall is bending, it is vertical and it is bending in this the vertical direction. Because of that only the shear force is coming. So you have to take the steel which we have provided in the vertical direction. Okay. So if you see, the AST which we have provided in the vertical direction is 8 mm dia bars at 125 millimeter center to center. Okay. So now for this purpose you have to provide the PT value. So PT value will be 100 into AST divided by B will be 1000 into D is 120. Okay. और यहाँ पर हमने क्या प्रोवाइड किया है, 8 डाया एट 125 सेंटर टू सेंटर. इसका AST कैलकुलेट करो, calculate the value of PT and calculate the value of tau c. I am sure it will be safe. Please complete this. बताओ पीटी कितना आ रहा है? सॉरी, 0.335 करेक्ट है. 0.335%. Okay, so your 0.335 comes under this. ओके, तो जो भी इसका इंटरपोलेट करके वैल्यू आएगा, डेफिनेटली दिस इज ग्रेटर देन द टाउ वी वैल्यू, एंड टाउ वी वैल्यू इज 0.138. ओके, तो ये जो भी वैल्यू आएगी यहाँ पर, दिस इज डेफिनेटली ग्रेटर देन टाउ वी, दैट इज 0.138 न्यूटन्स पर मिलीमीटर स्क्वायर. ठीक है, एज सच निकालने की जरूरत नहीं है, बट स्टिल एज अ डिजाइन प्रोसेस यू हैव टू कंप्लीट दिस स्टेप. ठीक है, so since tau c is greater, tau v is smaller, there is no need to design for the shear reinforcement. As such shear reinforcement वैसे भी नहीं provide करते हैं. If in case your wall is failing in shear, you have to increase the thickness of the wall. Okay, one way of doing this is you can increase the thickness of the wall at the bottom, and then you can reduce it. So in place of providing the straight wall, you can provide the trapezoidal wall. Okay, the bottom we have greater thickness, at the top we have smaller thickness. ठीक है, is it okay? Are there any queries? ठीक है, so we will continue tomorrow or in the next class with the design of roof door. ठीक है, let me stop the recording now. Let me mark your attendance first. Okay.